Hi, Kushal. Hey, Kushal. Just to check, are you hearing me? Hi, Shabnam. I was wondering if you are in the session. If you are, please share your audio and video. It should be a button on the right corner, top right corner of your screen.
Hi, Bita. You just cut off. Sorry. Can you say again?
Oh, can you hear me now?
Yeah, I can.
Okay, great. I just wanted to check if you can hear me or not, and if we have Shabnam, the speaker in the room or not.
Yeah, the speaker is yet not in the room. Let me just message Jen about it.
Okay, so she's not here yet because it's 1:20, and I believe we can, because we want to make sure that everything is right. So
Yeah,
it would be great
yeah,
if
sure.
you can. Thank you.
Yeah, no worries. Hi, Shabnam. Can you hear us?
Hi there.
Hello. How are you today, Shabnam?
I'm good, thank you. I'm so sorry to be looking away. My camera is set up somewhere else. How's my audio, by the way?
Looks fine.
So how about the audio though?
Audio is also good.
Okay, thanks.
Hi,
So, yeah,
Hi,
go
Deepa.
ahead.
hi. This is Beta, and just waiting for Kushal to do the tech check, and we can talk afterwards.
Okay,
Sorry.
sounds good.
Yeah. So, Shabnam, do you want to share your presentation once?
Yeah,
So we'll have a look at this going well.
sounds good. Just give me a second. The thing I had to come to the lab. So one thing that changed from yesterday to today is that I'm using multiple monitors, but they're from multiple computers. So I'm hoping that this looks good.
Yeah, it looks good.
Okay.
Do you want to move the slides? Is it going fine? I just want to make sure. Yeah, perfect.
Yeah. Okay.
Yeah. So, uh, at this time, the people will be starting joining us in a minute. So I will be leaving the screen, and Beta would be here to introduce you.
Okay. Sounds good. So
All
I
the best,
might as
guys.
well. Thank you so much, Rochelle. Okay. I might as
Thank you
well
so
go
much.
ahead
Bye bye.
and bring this
Hi,
up.
Shabnam. It's great to have you as one of our speakers. Nice to meet you.
Nice to
I
meet you as
would
well.
be great. I will be your host and I will be introducing you. I think people now are joining us. You can be on mute and I will introduce you and I will collect the questions for you and I will ask on behalf of audience at the end of the talk. And at the end, you can ask me any questions that you have.
Okay. Sounds
And
good. Just to
great.
last check, do you, because
Sure.
I've been told that my audio is often not really good when using this computer. Can you hear me okay? Is everything sound fine?
Yes.
Okay.
Yes, I can hear you. Okay. Everything is fine and I can see your share the screen as well.
Okay.
And
Sounds great.
great. I'm here
Okay.
if you have any questions, but I will be on mute until the 1:30, I believe.
Okay. Sounds good. Same.
Great.
Vita, can I just tell you something quickly?
Sure.
Once I go to my presentation mode, I will not be able to see you or any other, like I cannot monitor the chat, unfortunately, because I'm doing this
I'll do
multiple.
that for you.
So that's why thank you so much. If something arises or there's something going wrong, please let me know to just,
Sure.
if you unmute yourself, I'll be able to hear you, but I won't be able to see you, unfortunately.
Sure. Sure.
Okay, thank you.
And I also monitor the chat.
I appreciate that. Thank you.
Great. Hello, everyone. I'm seeing that you are joining the talk. We are starting the talk in just a couple of minutes. It would be great if you can let us know from where are you joining the talk, and we will start in just a few minutes. Hello, everyone, and welcome to the ML in Healthcare Summit. I'm Bita, your host for this talk. I have the great privilege to welcome Shabnam, one of our amazing speakers, this evening. She's a PhD candidate in the Institute of Biomedical Engineering at University of Toronto, a graduate fellow of Schwartz-Rissman Institute for Technology and Society, and a postgraduate affiliate of Vector Institute for Artificial Intelligence. Her PhD projects are focused on adaptive and intelligent systems for making automated vehicles usable by older adults with or without dementia to prolong their safe driving period. In these projects, she and her team use Driver Lab at University Health Network to empirically explore potential features that need to be incorporated in such intelligent system. Before starting, I just want to mention if you have any questions, feel free to post them in the chat section. I collect all your questions and make sure that we discuss them at the end of the talk. Without further ado, Shabnam, over to you.
Thank you so much, Bita, for the kind introduction. I just wanted to get a quick thumbs up that everybody can hear me. If I can use the chat or somewhere else to let me know, that would be perfect. But I can also move on, assuming that you all are hearing me and just not giving me any indication. But, okay, great. So it's a pleasure to present our project this is a project with Dr. Jennifer Campos and Dr. Alex Mihailidis, which is focused on a method of enhancing the usability of automated vehicles among older adults using driver state monitoring systems that can detect mode confusion. And I appreciate how this might be a mouthful, but I will be going one by one. I will cover main aspects of the project. First, the motivation behind why we're focusing on enhancing the usability of automated vehicles for older adults, and why this project is considered a project in health and well-being. Secondly, I'll talk about what exactly is mode confusion and how we have framed it in order to be able to use machine learning to be able to detect it. And third, I'll talk about our data collection, during which time I would like to make the case that, similar to other use cases of machine learning and healthcare, data collection is difficult, expensive, and in many cases, the bottleneck towards applying more sophisticated machine learning algorithms to solve the issues in healthcare and in ML. And at the end, I will give an overview of our results. So first, motivation. Why we are focusing on enhancing the usability of automated vehicles for older adults. There are two main incentives to promote the safe use of automated vehicles by older adults. One is road safety. Specifically, we know that there are reports that project that by 2025, age-related frailties will be the projected cause of fatal crashes. And secondly, another reason of promoting use of automated vehicles by older adults is to avoid or delay driving cessation, which we know from the extensive literature on this. Driving cessation can have significant adverse health consequences for older adults, which range from faster cognitive decline to increased risks of institutionalization to even threefold increased risks of morbidity. Now, it's no wonder really how automated vehicles have generated this excitement on how they may be able to solve these issues and support older adults to drive safer and longer and thereby avoid the health consequences of driving cessation for them. So in this sense, we are considering automated vehicles to have the potential to be an assistive technology, really. But what do we mean by automated vehicles? All automated vehicles are really an umbrella term that describe all the vehicles with different levels of automated functionality. And this, what you are seeing on the slide, is the most formal categorization of different types of automated vehicles, which is based on technical plausibility. So in this sense, each of these levels are the steps that the industry is taking towards achieving that holy grail level 5 here, which we often call or hear in the news as autonomous vehicle or driverless cars. But if we consider this 2D space, 2D grid word of all the possible types of automated vehicles, if you will, autonomous vehicles are really just this one dot in this 2D grid space where these types of vehicles can perform all types of all tasks of driving under all driving conditions, so 100% of driving conditions. But the rest of automated vehicles will fall somewhere here, where they cannot perform all driving tasks at all times. So it's important to know that for many reasons, we are a long way away from that autonomous vehicle. These reasons can range from policy legislations to consumer acceptance, etc. So for the time being, at least, we are left with automated vehicles that can perform some driving tasks under some driving conditions, and then some other driving tasks under some other driving conditions. And what this means is that for the time being, the functionality of an automated vehicle depends on the driving condition, which again means that a given automated vehicle may have multiple modes or states of operation, which from the user or driver perspective, it makes more sense that to view automated vehicles not in terms of the levels of technical plausibility, but in terms of different modes or states. So put it in a language that I think the attendees may appreciate. We can look at this as a sort of like a Markov chain with finite states, where moving to this, where the number of modes or states in an automated vehicle and the probability of transitioning between these states could be different from one automated vehicle to another, from an automated vehicle from company X to an automated vehicle from company Y. So our framework really explores how these distinct state structures for each automated vehicle, what does this mean for the driver and specifically for an older driver? So imagine a driver, such as an older adult who has used a non-automated vehicle so far, and is now transitioning into using an automated vehicle with M modes of operation, where each of these modes, as you see on the screen on this left-hand side, can have a distinct set of responsibilities for the driver. So the driver needs to know two things to be able to safely use this automated vehicle. One is that he or she needs to have a general awareness of the number of modes in the vehicle and what each of these entail, which we call state structure. And secondly, the driver needs to, at any moment in time, know what the current active mode of the vehicle is and to know their corresponding responsibility. Borrowing from the aviation literature, these two types of mode awarenesses are called type 1 or general mode awareness, and the second one is called just transient mode awareness. I'm not going to go into details of this, but for our purposes, to explain the framework, it is important to note that mode confusion is essentially this lack of type 2 mode awareness or being confused about the current active mode of the automated vehicle. And we expect this mode confusion to be more likely among older adults, as it draws upon attention resources that could be affected by age. So the safety risk of mode confusion arises because each AV mode requires a distinct set of responsibilities from the driver. So if the driver's perception of the active mode of the automated vehicle is incongruent with the true active mode of the vehicle, as is the case in mode confusion, this means that the driver is simply not doing what they should be doing. In fact, a couple of recent crashes involving an automated vehicle has been linked to mode confusion. So to be able to detect mode confusion, our proposed framework is really based on this hypothesis over here, that the driver's perceived AV state or mode influences how they monitor the environment and how and their level of mental workload. And we further hypothesize that we may be able to capture these trends by using the gaze behavior data from the drivers. So kind of reverse engineering it again, what we're saying is that we may be able to infer drivers' perceived AV state from their gaze behavior data, and in that case, we will be able to compare it to the true state of the AV and declare any incongruency as mode confusion. And so, as you know, any problem is really solved when the question is reframed. So this is a reframing of this mode confusion question in a formal design of a state monitoring system, where if you look up here, the system is expected to have two general inputs. One is the sequential observation from the driver, which consists of the gaze behavior data from the driver. And the second input is the true AV mode, which is plausibly assumed to be known to the driver monitoring system because it's known to the automated vehicle. Now, with these two inputs, so if we can infer the perceived AV mode, the driver's perceived AV mode, then here, by comparing the perceived and true AV mode, we should be able to detect mode confusions if these two are not, if these two do not match. For that inference, we are proposing to use classification algorithms to classify the features of gaze behavior into all possible modes of automated vehicles. And the rationale here is that by definition, in the mode confusion, in an instance of mode confusion, the driver is assumed to know the possible modes of an automated vehicle. So if the driver is confused, this means that she or he has taken one mode for the other. And I'm happy to go more into details of this because I appreciate it's very complex at first sight. Now I'm going to describe how we collected the data that we applied this framework on. Specifically, we had 36 older adults ranging in age from 65 to 90 years old, who were self-reportedly healthy and they had driver's licenses. They tried full automation and non-automation in a high fidelity full field of view driving simulator. But it's important to note that we actually couldn't use, due to technical difficulties, a number of the data that was collected. So we ended up with data from 29 participants, which times to this 6 scenarios yielded 174 time series of gaze behavior data, and each of which were about 7 to 9 minutes in duration. This is the driving simulator that we used, and I'm hoping that on the screen you're seeing the dome that the driving simulator is in. Inside this dome is covered all around by projectors, which you see on the picture on the right hand side, and the vehicle can actually is on a turntable inside this dome, and the vehicle can turn around all over. Now, moving on to the inside of the vehicle. So here you see that inside that dome there's an actual vehicle. It's an Audi with all its internal components intact. So when the participants came in, they experienced different driving conditions and specifically 2 modes of automation, so non-automated and fully automated, which means that in our framework, our problem was reduced to a 2-class classification, which made sense because this is the very start of solving the problem of mode confusion. So it made sense to start with the, I guess, simplest classification model. Now, in terms of the results, before I move on to the results, sorry, I need to note that it's hard to see the cameras here, but there are 4 cameras mounted inside the car. So these were used to non-invasively collect the gaze behavior data that we used. And what we did with this data was to extract 25 features related to drivers' monitoring behavior, one of which is a novel one that we introduced, but almost all of these features are related to 2 pillars of our gaze behavior. One is known as fixation, or the locations on which we fixate our attention to get information, and the second one is called saccade, which is the rapid eye movement between locations of interest. So there's a whole lot of literature on how these 2 relate to our monitoring behavior in driving or in other tasks. But I'm happy to go through those during the Q&A. But for the purpose of this, it is important to just have a good idea of what saccade and fixations are. So for instance, on the right side, you're seeing a figure of the fixation locations of one of our participants during their 9-minute drive. So these are the locations. So the average of these locations in one cluster, if you will, that are weighted by the duration where the driver was focused on that location in this 3D word. So the proposed the feature that we propose is essentially the entropy of these fixation locations weighted by the duration that the driver fixated on that location, which this feature is called. So this is a I guess a variation of a widely used feature that we called weighted static gaze entropy. Using a feature selection method, specifically maximum relevance, minimum redundancy, we ranked the 25 extracted features into ranks from 1 to 25, where our proposed feature of weighted static gaze entropy was ranked first. And for those who are not familiar with MRMR framework, this is used in this framework. Metrics such as mutual information or F-scores are used to iteratively choose the most relevant feature, and a bag of features to the class labels, while at the same time this chosen feature should have minimum redundancy with the rest of the features, as I think as measured by Pearson correlation. This is introduced in 2005, but it again rose to fame in 2017 from a paper by Uber. Now here you see moving on, here you see that this is a result of applying one arbitrary classification. This is specifically is LDA on increasing number of features. So to note, our bag of features, our data, our sample was only 174. So you'll see that the pattern here in this figure, that with the increasing number of features, the classification performance dropped. So we use this visual inspection relay with using similar figures for each classification algorithm to choose the optimum number of features resulted for that classification using tenfold cross-validation. And here you see that using this chosen optimum number of features for a number of classes, here we report the results of tenfold stratified cross-validation. And using the metrics of accuracy, area under the curve, and F1 score, you see how the last one actually, the ensemble of classification models 1 to 8 over here, led to the best performance. Especially of interest to us was the area under the curve, which led us to conclude that the gaze behavior data could in fact be used to differentiate between perceived levels of automation from the drivers. But I'm going to take this last minute to talk about the limitation of this experiment, and which is essentially the limitations that our data posed to us. First and foremost is that the data included gaze behavior data for only 2 modes of automated vehicle, which resulted in 2-class classification. Future research really needs to apply this framework on data from more modes of modes of automated vehicles to be able to test the efficacy of this framework. In addition, the data, as I described, was collected in a simulated automated vehicle, so in a driving simulator. And future studies really should test the validity of this framework by applying it on real-world road data, because the monitoring behavior might as well be very different. And the major limitation of this is that this testing and experiment will remain as a proof of concept, really, because no instances of mode confusion was used to be able to validate our last hypothesis. It's just a stepping stone towards solving this issue. With that, I would like to thank you all for listening, and I'll take any questions that you may have. Thank you.
Thank you so much, Shabnam, for the great presentation and interesting talk. Let's take the questions. Please feel free to ask your questions in the chat section, and I'll make sure to ask all of them to Shabnam. One question is that which one of the classification algorithms you've used for confusion model perform better in terms of the area under the curve?
So this it was the ensemble. Let me bring it up. So, or just I might as well not just share this again. But so it was the ensemble method of like stacking the classifications of multiple classifications, really: LDA, QDA, AdaBoost, random forest, Gaussian process, SVM, logistic regression. So just stacking these all together resulted in a higher AUC plus the test accuracy. But if you want to just go with the most simplest version, LDA surprisingly perform the best if we take AUC solely. So that was good, surprising.
Amazing. Thank you so much. And Salim asked that would this be considered a novel research or perhaps a novel application towards helping the elderly?
Yeah, absolutely. So I know for a fact that companies such as Renault, like Volvo, are really focusing on mode confusion per se. So the topic of interest, because it's a safety concern for automated vehicles. But as it relates to older adults, as to the best of my knowledge, it is a novel application because, and this is part of the reason why I talk about the motivation, because it's important for companies, for us to think about good applications of automated vehicles for enhancing the mobility of older adults and help. Yeah.
Thank you so much. And another question maybe is that beside from gaze behavior that you've mentioned that you've used as sort of features, did you consider or do you have any plan to consider other features like, I don't know, like facial expression and things like that to see what is happen? And do you think it will affect the model accuracy, maybe enhance that?
Great question. Absolutely. I'll just preface this with one other consideration is that we only compared two modes of automation, and with increasing modes of automation, the interactions of the driver and the vehicle becomes increasingly constrained, I guess. So other types of data, such as like, if that is to say, if we include another mode that is in between full automation and no automation, we may even be able to use other sources such as how much they are engaged with how they use the steering. So, but to your point, I think face videos are a great idea, and we actually have them collected. The only reason we steered away from it was just to test this, because it's less computationally expensive to design something on vehicle that doesn't process video. But absolutely, it would be a great future direction.
Thank you. Thank you so much, Shabna, for the great presentation. And thank you all for attending this talk. Thank you so much. I just want to let you know that we will get a short break and we will be back in 20 minutes for the next series of talks. So thank you. Thank you so much.
Thanks, Peter. Bye, everyone.
Thank you. Bye.